All right. So thank you very much, Eric. I'm quite honored to be here, and I'm glad to have an opportunity to sort of give an extended overview of a project I've secretly been working on over the last 5 years now. And I'm going to begin with a little story. So many of you know that I help with this programming language called Kotlin. I've been doing so for 7 years, but actually it was many years until I met anyone from the team. But one day, Andre Breslov, the head of the team, and I happened to be in town, or in the same city together, so we met up for breakfast. And what Andre wanted to talk about was Java. So one of Kotlin's major selling points is that it's highly interoperable with Java. And he said this was working great, except for one thing. Null pointers seem to be gumming up the works. You see, in Kotlin, when I say string, I mean string, not null. If you want it to be possibly null, then you use a different type, string question mark. You be explicit about your nulls. And you can't assign between these types because Kotlin is a null-safe language. And this is well liked within Kotlin code, but it causes problems for interacting with Java code because in Java, a string might be null. But they didn't want Java programmers, or they didn't want people working with Java libraries to have to always be checking null pointers because those Java libraries weren't designed with this type system in mind. And they didn't know what to do. So I stuffed my face full of food, thought about it for a little bit, and then proposed this string bang type. What is string bang? Well, it's a string that might be null. Nothing new there. In fact, you can assign it to and from string question mark. So you might ask, what's the difference? Well, the difference all comes down to perspective. With string question mark, we're saying, well, there's a possibility this is null, and be pessimistic about it. Make sure I handle that case. With string bang, we're saying there's a possibility of being null, but let's be optimistic about it. Take advantage of the fact that the programmer using this probably has years of experience and might actually know better than the type checker when it's okay to assign this to a string. But don't completely trust them. People, even experts, make mistakes, so do a little null pointer check at runtime. So Andre liked this idea, but there's a clear oddity in this picture. We've said that you can't assign string question mark to string, but clearly you can through string bang. So what's going on in this weird type system, and what's the intuition for how we should implement it, since after breakfast he has to go off and program it? So I stuffed my face full of food again, thought about it for a while, and then came up with what I call the optimistic perspective. So the idea is type checkers are inherently pessimistic. If I have a single assignment of string question mark to string that has a possibility of not working out, I reject this code. And in many ways, this is good. It can help us find a bug or make sure that we're using the library correctly. But it can also disrupt our workflow when we know that possibility isn't going to happen, or it's at least unlikely to happen. And so what optimism does is it gives programmers control over this. It lets the programmer tell the type checker, hey, I know what I'm doing here. Let's just try it anyways. And you can always double check me at runtime to make sure I'm actually doing what I think I'm doing. And so in this mindset, string bang is what I call an optimistic type. That is, string bang represents two possibilities, and we optimistically choose whichever possibility for a given situation makes things go through. And so if you ask the question, well, should string question mark be assignable to string bang? The answer is yes, because I can interpret string bang as string question mark, and this would work out. Similarly, if I ask if string bang should be assignable to string, the answer is yes, because I can interpret it as string. And this perspective also lists to higher constructs, so I can ask, well, should list of string bang be assignable to list of string? And again, the answer is yes, because we can interpret that string bang as a string. But we're not allowing just everything to happen. So for example, you can't assign an integer to string bang, right? Our optimism is scoped or bounded in a sense. Now, many of you might recognize this relationship. It's very closely related to consistency, or more precisely, consistent subtyping. And this whole optimistic perspective is very reminiscent of predicate lifting. And these three works I referenced, or these three concepts, come from the gradual typing literature. Because what we're doing here is actually applying gradual typing to Kotlin. It's an unusual application, but one that's actually essential to the adaptability of Kotlin, even though Kotlin's major selling point isn't its type system. So gradual typing isn't necessarily tied to simply adding types to languages. Okay, so let's take a step back and say, what is gradual typing? Well, in general, the goal of gradual typing is to let typed and untyped code be mixed together, and yet still provide some guarantee about how that mixing works out. In Kotlin, we interpreted typed as null safe and untyped as null unsafe. And the guarantee we intended to provide was that a string was a string, not null. So why would you care about gradual typing, besides the example just showed? Well, very often it's motivated by saying, well, there's a lot of untyped code out there, and for a variety of reasons, sometimes we want to add types to this code. But I'm actually not going to focus on this motivation. I'm going to focus on the other common motivation, which is the flip side. Namely, there's a lot of typed code out there, but sometimes types suck. They just get in your way. So what are some examples where types serve as obstacles rather than aids? Well, suppose you're learning to program. And the education community will tell you that experimentation is very valuable, but you can't experiment and run your programs in a type language until you can figure out how to make a type check. So types are obstructing your experimentation. Say you're interoperating with other systems. Often those other systems are untyped or have a different type system. And so there's a lot of overhead involved in wrapping up those objects in your own language's type system. When you're scripting, often these programs are intended to be short-lived, so you may not need the infrastructure of types, and often they're interacting with, again, untyped systems. So types just can get in your way repeatedly. And when you're prototyping, the whole point is to sort of keep playing with your code and see what its structure looks like. And that informs what your type should be. But if you're required to have your types from the beginning, then you're forcing the programmer to do things in the wrong order. Okay, so looking at all these applications, or looking at all these domains, there's another interesting observation, which is although types do get in your way, they can also still help you out. So for example, in education, not only are you learning to program, you're also learning a vast set of libraries. And types can provide a convenient way for talking about those libraries and navigating through all the documentation. When you're interoperating with other systems, although the code you're interoperating with, or all the data you might be interoperating with might be untyped, what your operations you're doing on it are structured things like collections and maps and stuff like that. And in fact, in say C#, the recommended way to do JSON code is to use this library json.net, applying C#'s dynamic type, or gradual typing. When you're scripting, you're often working with a wide set of APIs that you're tying together. And it's not always easy to remember what exactly that method name is, but types can help an IDE remind you that it's get element by name, not get element by ID, for example. And when you're prototyping, you're making changes to your code, and what's common change that you want to make? Refactoring. And types are essential components of how IDEs can help refactor your code for you rather than requiring you to manually go through everything and update it. So in all these applications, although types although you may not want to write types yourself, it's still useful for your code to be sitting on top of a typed infrastructure. And 5 years ago, I decided I wanted to target these kinds of applications. And I would sort of codify that by saying, for the gradual type system I want to build, I'm willing to assume that I'm building this gradual type system for a language in which most code is typed. So say all the stable libraries are typed, or the internals are typed, but the fringe can still be untyped. Now, what's a well-known example of code of a language where most code is typed? Well, Java. And we actually can learn from Java. Specifically, we can learn from raw types. So why am I talking about raw types? Well, here's some Java code where we set up a list of integers, we add a string to that list, and then we try to get a string out of it. Now, there's an obvious bug in this code, but let me get to that later on. First, does this code type check? The answer is yes, although it's a little odd because here we have a list of integers, and here we're saying, oh, let's just treat it as an arbitrary list that I can add objects to. And this arbitrary list is known as a raw type. It's the old way to refer to lists. And when Java added generics in 2004, there was already millions of lines of Java code, so they needed some way for this new generic Java code to interact with the old, all these pre-existing libraries. And so applying our optimistic perspective, what they essentially decided to do was view raw lists as lists of dynamic, where dynamic is optimistically whatever type you want, and including integers, so this assignment is valid. All right, so that's why this code type checks. Now what happens when we run it? Well, clearly we're going to get an error. But where would you expect that error to be, and where does it actually happen? Well, in this case, it happens when you try to get an integer out of a list of integers, which doesn't make sense because that's a perfectly well-typed operation. Where you and I know should be going wrong is in this line, we're adding a string to a list of integers. And these kinds of errors that actually sort of mislead you, tell you that the fault is here rather than over here, was actually a major problem for Java when generics were introduced, and still causes problems, but thankfully raw types have been reduced in popularity by this point. So a goal of mine, based off of this, was to have what I call an accountable gradual type system. That is one where errors can correctly direct you to the code that's sort of causing problems, or at least the interface points that are causing problems. Now, this concept is not my invention. You probably know it as blame, and it actually comes from the contracts literature, but was adapted to gradual typing in the form of typed racket. And then later in 2009, shown that you can implement this in a way that actually guarantees accountability. Now, how did they do this? Well, let's go back to our Java picture. What they did is said, hey, well, in this line of code here, we're sort of changing perspectives. We're going from this pessimistic perspective of a list of integers to this optimistic perspective of a list of dynamics. And that optimistic perspective isn't correctly enforcing the pessimistic needs. So what we can do is, behind the scenes, insert a little wrapper. That is, make a new optimistic list that, before it gives anything to the pessimistic list, dynamically checks whether those pessimistic needs are satisfied with this, say, cast to integer here. And by doing this, now we try adding a string to this list. We get a class cast exception in the method call where you'd expect it because of this cast to integer fails. So wrappers are a great way to achieve accountability. However, they come with another set of problems. So for one, we're inserting an allocation here. And any experienced, say, Java programmer knows that allocations are something to be wary of. They can introduce a lot of overhead, and so maybe there's an efficiency concern here, which we'll discuss later on. For another, there's some semantic questions. What happens if later on I ask whether strings is referentially equal to ints? Well, if you say the answer should be yes, how do you implement that efficiently in a backwards compatible manner? If you say the answer should be no, well, how do you expect people to reason about referential equality if these wrappers are being inserted behind the scenes and they can't even see this happening? So rather than answer either question, I decided that given these concerns, I wanted to have what I call transparent gradual type system. One that doesn't insert things like wrappers. It simply inserts little runtime checks like, say, null pointer checks that we're all used to. But I still want my system to be accountable. So how do I achieve that if I can't use wrappers? Well, let's revisit the assumptions. I already assumed that most of my code is typed. So it's not unreasonable to further assume that most values can know their type precisely. That is, unlike in Java, where a value would only know that it's a list, causing that delay of errors that we saw earlier, I believe that you can have a system where values would know that they're lists of integers. And thankfully, there's already a language out there that implements this and is widespread, namely C#, and it even already implements gradual typing. So let's take a look at C# and see what we can learn from it. So here's a program, snock, the cons backwards. And it's a generic method. And you can snock a singleton list hello with an element 5 and get this list hello 5. But suppose I'm not comfortable with generics yet. Suppose I'm still learning all this stuff. And rather than achieve polymorphism by using generics, I decided to achieve polymorphism by using dynamic typing. Now I run my program, I get hello 5, but in fact I get runtime error, even though this is essentially the same program as I had before. So imagine if you're a beginning programmer, would you have any ideas to what's going on here? I mean, probably a number of you don't know what's going on even as advanced programmers, but some people do. So let's step back and look at our typed code again, and let's take some more time to understand why this code was well typed. So the first thing is, we have a generic method, so it has a type parameter t. Consequently, when we call this generic method down here, we have to actually figure out what the corresponding type argument for t is. And we do this by looking at the arguments and saying that the first one is an IEnumerable of string, and the second one is an integer. Now, there's no common t between these two types in this current form, but we can take advantage of subtyping and realize, well, this integer is an object, and IEnumerable is covariant, so this IEnumerable string is also an IEnumerable object. And so we can infer t to be an object, or object. And thus we can type check this call to snock. What about the body of snock? It actually also uses a generic method, namely toList. So what's the type argument for toList? Well, once again, we see that start is an IEnumerable of t, so the obvious type argument of toList is t. And now we fill in these holes in our code, makes a type check, and we print hello 5 when we run it. All right, now let's go back to the dynamic version. Well, first thing is snock is no longer a generic method. It doesn't have a type parameter. So this snock of object is useless. It's just snock now. And secondly, this type t is no longer in scope. So we can't have this around. We actually have to figure that out at runtime. And how do we do this? Well, we execute our code. We eventually reach this point and ask, at runtime, can we infer the type argument for toList? And so we look at what the value for start is, namely singleton hello. See that its runtime type is IEnumerable of string, and so the obvious thing to infer is string, as opposed to object like we did before. And consequently, this method, when it returns, gives me a list of string. Now what happens if I try to add 5 to this list of string? Well, we get a runtime error, because you can't add an integer to a list of strings. And that's the cause of why the program doesn't work anymore. Now, this is complicated enough. I don't want to have my users of my language have to do all this reasoning to figure out when they can use dynamic typing and when they cannot. Instead, what we'd like is that if I have a well-typed program that runs in a certain way, then the dynamic version of that program should run a similar way. That is, I'd like it to be what I call reflective. The dynamic semantics, dynamically typed semantics reflect the statically typed semantics. Technically, they actually can improve upon the semantics because dynamic typing can execute things that statically typed code won't even accept. And this is a property of runtime behavior, but there's a similar property of compile time behavior, which is that if I have code that type checks statically, well then inserting dynamic, that is telling the system to be more optimistic, should still type check. So adding dynamic should improve the typability of your programs. And so we get this list of goals for a gradual type system. And this list might look familiar because I'm not the first to come up with it. Transparent is a little new, but most of the list has actually been around for a while. You can even find it in the typed racket work I referenced earlier. And this list is still being understood. So for example, just recently, or I guess 2 years ago now, these last two properties were formalized as the gradual guarantee. So now we have this list of goals, and we've seen that C# doesn't satisfy this list, or it fails to achieve this. But let's get a better understanding of why C# fails to achieve this so that we can sort of learn from the mistakes. So here's another C# program. We have this getter interface that gets us values. We have this class 5 that lets you get integers and lets you get strings. And now we have this code that makes a new getter int from a new 5 and then prints out the value you get from it. And what does it print? Well, it prints 5. And now what happens if I do this dynamically instead? Well, once again, you'd expect print 5, but once again, you get a runtime error. And why is that? Well, we're type checking this code dynamically. So rather than using the static type getter int that we had before, we're going to use the dynamic type for this getter, namely 5. And with this dynamic type, this get method is now ambiguous. There are 2 get methods that can apply, and so C# actually throws an error. You might say, why not just make a guess? Well, I can always just change which one you do and avoid or cause the same problem either way. So the fundamental thing here is that we've essentially gotten a more precise type, 5, but for some reason that additional information made so we couldn't type check our code anymore. And so to be able to be reflective, what we see is that we actually need to make another assumption about the language we're going to add gradual typing to. That is, we need this language to have the property that if I give the type checker better type information, then I improve the typability of my programs. Okay, now let's also look at overloading. Here we have something that simply checks whether 2 objects are equal. We give it these 2 integers, but these integers get wrapped up in different ways, and so when we run this, we get false. But now what happens when I dynamically type check this code? Well, now if I run this, I get true. I've completely changed the semantics of my code. Why is that? Well, these have dynamic type int, and the overloading for equals equals is different for objects and integers. For objects, it does shallow equality. For integers, it does deep equality. And so we get false versus true. And so the key problem is, given integer equal integer, there's 2 ways to type check this. One is as 2 integers being equal, and the other one is 2 objects being equal. And these are giving different semantics. So if we want to have a reflective system, we need to have another property, which is that all typings will produce the same semantics. Okay. So, I'm ahead of time. So at this point, what we've been doing all this time is just requirements engineering, right? We've just been looking at the problem, understanding the use cases, working through how things are working and not working. And particularly, we look at specifically these applications and decided that the best way to represent these applications was through the assumption that most of our code would be typed. And then we saw that in order to achieve this nice property, this predictable behavior of accountability, well, then we need most values to know their type precisely, at least if we also want to have transparency and efficiency. And then we saw from C# that if we want this program to be, or this language to be well behaved, that is, be reflective and optimistic, then we need better types to imply better typability, and all typings to produce the same semantics. And then there's one more thing we need, and I know there's a glitch here, I forgot to fix it, which is that now we're going to be doing all this type checking at runtime. So what do we need our type checker to be able to do? Well, our type checker needs to be guaranteed to terminate. That is, we need type checking to be decidable. And then there's the glitch. So looking back at this list, there's a sort of chain of reasoning that falls from most code being, the assumption that most code is typed, and this goal of having sort of predictable behavior for a gradual type system. But if I were to pick one link in this list that is sort of the easiest to break, I would say it's this one, that most values know their type precisely. You can imagine other ways of doing this. But recently there's been a lot of studies about efficiency of gradual typing. And so one in particular is that, what, a year and a half ago, Takikawa et al. Sort of decided to do a thorough examination of how typed racket, or gradually typed racket, performs on various benchmarks, including the snake benchmark from their racket suite. And so first, you check the untyped case, and you check the fully typed case, and you see that, at least at the scale I'm showing it, these are pretty much the same, which is great. Gradual typing isn't causing huge problems in performance for these two extremes. But then they said, well, the point of gradual typing is to have typed and untyped code be mixed together. So what happens if, say, only half of your modules are typed and the other half are untyped? And so to explore this question, they took Snake and came up with every possible interleaving, or every possible combination of typed and untyped modules, and ran their experiments, and this is what they found. So as you can see, Racket blows up. While it works well in the endpoints, this sort of quadratic fit here shows you that the more mixed type it is, the more partially typed it is, the more overhead you achieve, or you see, to the degree of like factors of over 20 in the average case. This is clearly concerning, right? This is not going to be adoptable in practice. Now, they're working on fixing this, but in the meantime, we decided, well, there's other languages out there that also implement gradual typing, such as, say, C#. How does C# work on this? So we ported Snake over to C# and ran the same experiments, making sure to keep things fair. And this is what we got. So this is still a quadratic fit. It just looks like a straight line. And so C# is avoiding these cases of significant overhead. You get this nice linear transition from untyped to typed, which is kind of what you would expect, right? Each time you add types, you enable more optimizations. And from what for our examination, this difference of behavior comes from the fact that C# is a transparent gradual type system, whereas Racket is not. Racket has wrappers, and it seems that those wrappers are actually causing a lot of overhead, as we were concerned about. But C# has its own problem. Look how slow the dynamic type version of C# is. It has 10 times overhead, approximately. This also is unacceptable. I mean, even if we get to mostly typed, it still has significant degrees of overhead. So while it doesn't have the worst cases of Racket, it also is sort of missing many of the best cases of Racket. And so there's still, and looking into how this all is implemented, it seems the reason for this is because C# is not a reflective gradual type system. And this causes them to have to implement it by literally recompiling the code every single time they get a new value, because they can't compile their code until they actually know the static types of everything to figure out what the semantics of the code should be. Okay, so seeing this problem, Tate et al. Decided to try a different approach to implementing gradual typing. They did what's called a monotonic, transient approach, which is also a transparent system. And so they tested this on Python, and these are the numbers they got. Now I'm only showing the fully untyped and fully typed case, but as we saw with C#, the same argument applies for them, that they're going to have a smooth transition between these two. So the middle cases aren't so interesting for this one. And you can see that the worst case overheads are much better than the worst case overheads previously. But there's something else that's weird here. Namely, if you're adding, the typed code is slower than the untyped code, often significantly slower than the untyped code. Now they're trying to achieve other things, like they're trying to make sure that their code still works out even if other people manipulate their objects. So there's some good reason for this. But nonetheless, they're punishing programmers for adding types to their code, which is not exactly going to get programmers to add types to their code. So based off of this, I decided that another explicit goal of ours should be that we have a motivating type system. That is, our types will improve performance, so programmers are encouraged to add types to their code. Okay, looking further, there's another paper that works on having efficient gradual typing for Typescript. And this is what they get. Now, you can see in their fully typed code, they only get 6.5% overhead, which is great. And what's interesting about this is that they also are a transparent system. And in fact, values know their type precisely. They have optimizations for adding this type of information only when necessary, but values know their type precisely. And yet they still are getting this overhead of 22 times to even, on average, to up to 72 times in the worst case for their Octane benchmarks. And note that these benchmarks are sitting on top of typed code. Like this is the core of Typescript is typed. And so they're getting overheads from this interaction between the untyped and typed pieces. And it seems that this overhead is coming from the fact that although these values know their types, those types are represented structurally, which makes them expensive to construct and also expensive to check. And so going back to our assumptions, this sort of suggested that we should refine our assumptions to saying that most values should know their nominal type precisely, because we can do runtime checks and runtime nominal checks quick and efficiently. Okay, so now I've caught you up to where I was about 5 years ago. This is the list of assumptions I decided to make and the goals I wanted to go for. And there's a glaring problem with this list. So gradual type systems are usually added to existing languages, right? You're trying to give some system more flexibility. But let me ask you, do you know of any type languages that satisfy all these properties? We've already seen that C# doesn't, Java doesn't, Haskell doesn't. I'm not going to bother going through a list, but the answer is no. At least none of the major languages satisfy all these properties. And particularly these last three properties, something always goes wrong. Now, why is that? Well, we often think of typed languages as things which check types at compile time. But typed languages do more than check types. They also use types. For example, Java uses types to figure out which overloading to dispatch to. C# uses types to implement their generics efficiently. Haskell uses types to infer the semantics for the type classes. And this makes sense. They already have all this type information there. Why not take advantage of it rather than just force it? And so there's nothing wrong with actually using this type of information, but as we've seen, gradual typing isn't always compatible with this. The reason is that if you have all this information available statically, there's enough context for you to infer intent. But dynamically, you don't have all that same context, and so you can't infer intent in the same way, and you get these differences that we've been seeing. And so all this work I've done so far, or everything I've shown you so far, is basically an effort to convince you that you can't simply gradualize any language. Instead, gradual typing has to be made a part of the language, at least if you want to target typed languages. It has to be part of the design from the get-go if you want efficient performance and well-behaved semantics. And so 5 years ago, I decided that I wanted to, instead of exploring adding gradual types into existing systems, I wanted to work on co-designing gradual type systems with all the language features that we're used to in common practice. And I'm not expecting this language that I'm building to actually be used, but even if it's never used, what you can learn where things will go well, where things will go wrong. You can inform designers what kind of trade-offs there are if ever they want to add gradual typing. It can inform programmers where to be wary of gradual typing for languages like C# that provide this kind of features. And so currently I'm just exploring how could I say implement overloading in a way that is usable in practice, that way that is it satisfies its common needs for overloading, but it's still but it's still compatible with gradual typing. So I'm just going to dive in and give you a peek at what I've actually been doing for the last 5 years. And we'll start by looking at, say, string builder. So with string builder, the key method is this ability to append strings, right, and build up a giant string. But string builders are often used in code that needs to be efficient. That is, needs to scale up because you're going to be appending lots of strings. And so it's worthwhile to specialize this append operation to various common cases. For example, sometimes you just want to append a single character. Now sure, you could turn that character into a string and then append that string, but there's an allocation there that doesn't need to happen, and we've already seen that allocations can cause significant overhead. So we'd rather just have something that can directly take a character, tack it on, and move on. Another thing you might do is say append the results of another string, or the current state of another string builder, which allows you to directly copy from the internal array of that string builder to your internal array, which is much faster than converting to strings in the middle. And so this is a little toy example of what overloading can look like in practice. And what's nice about this example is that all these different overloadings are disjoint. That is, no value can be appended by multiple overloadings. At least that's what we would like to think. But what about appending null? Right? Well, nulls could be viewed as a string, or nulls can be viewed as a string builder, for example. So if I append null, there are two different ways to dispatch to this. And again, we're doing this this null might appear at runtime and it'd be dynamically type checked, and we don't have the static type information available to figure out which overloading was intended by the programmer. And so we have to remember that we said earlier we need all typings to produce the same semantics. Now, ideally, a good library designer is going to have the same behavior for both these cases. But we don't want the behavior of our gradual type system to rely on programmers implementing good practice. Sure, programmers often implement good practice, but they often don't sometimes too. And so I decided, well, null pointers have already cost us $1 billion. They've already robbed us of the soundness of our systems. So why don't we just get rid of them? Or at least make it so that null is not a string and null is not a string builder. It's its own value. You have to handle it explicitly, just like we did in Kotlin. And so if your string builder wants to provide the ability to append null, well then you just provide an append null case. And now this case is still disjoint from all the remaining cases. If you don't want to append null, you want to throw an error, well then you just rely on built-in techniques for throwing errors for nulls. So now we have these disjoint cases here that are actually disjoint. But there's more to this picture. So imagine one very common usage pattern for this. I can tell you the piece of code that you will see extremely often with this design, which is builder.append something.toString. You're going to see this over and over and over again. And do you really want your users to have to deal with this all the time? Well, no. So you're going to provide another overloading, one for just arbitrary objects. And now we have a problem, because object is not disjoint with string character or a string builder. Well, in some languages it's disjoint with character, but not in ours. So how do we resolve this? Well, one thing to note is that while object's not disjoint from them, it's a supertype of all of them. So if I were to give you some type, I can still tell you what's the best match for this type. Right? There's a guaranteed best match happening here. And this gives us an idea of what to do, but we still have to be careful. That is, suppose I were to assign a string to object and then append that object. Well, this will resolve to the append object overloading. But now if I do this dynamically, this is going to resolve at runtime to the append string overloading. And so once again, we're running into the problem of different overloadings being dispatched to by the static versus dynamic semantics. And we want our system to be reflective, right? Dynamic should do the same thing as static. So what can we do? Well, we can, when we have overloadings, we can dispatch the overloading not only based on the dynamic type of the receiver, but also based on the dynamic type of the argument. And say, well, dynamically, this isn't a string, so let's actually call append string. So people probably recognize this. These are known as multi-methods, and it's particular principal multi-methods. That is someone that is, for any given value, there is a best match for that value at runtime, if any match. But multi-methods have some known problems with efficiency, and we've already seen problems with efficiency, so how can we try addressing those problems? Let's think about how we can implement this. So first, how do we represent an object in, say, our runtime system? Well, remember, we've assumed that most of our code is typed, and most values know they're typed precisely. So we should probably base our implementation off of what objects look like in typed languages. That is, we should have this meta information link at the top, and then the field values below it. This meta information will point to a lot of things we're used to, right? It'll give you the nominal type for the object, the virtual method table for the object, and the interface table for the object. Just like standards, that way when we're using it in our statically typed code, we can execute it just like we would a normal statically typed value. But sometimes we're going to execute it from our dynamically typed code. And so what we do for this? Well, one way is to sort of look at all the meta information for this and then dynamically figure out what the best match is. And that's what C# sort of has to do. But what we can do is just add another case to the table. That is, we have a dictionary that's a standard lookup. Here's the method name, what's the corresponding implementation. And we just call this dictionary whenever the receiver was dynamically typed, just like we would if we were, say, in JavaScript or Python. And I'm not the only one to come up with this. The Gradual Talk people actually came up with the same optimization to make their code work out well. But what we can do is also even extend it to virtual methods. That is, our virtual method table could have entries for the general case and the specialized case, and because of the guarantees about the principality, you can jump to the specialized cases statically when you happen to know statically which one is best, even with inheritance and all this stuff. And so to test this out, to see whether this strategy actually works well, we revisited this snake example. We made our own little toy language, nom, both because I eat a lot and because it's based on nominal types. And we ran the same snake benchmark through it, and this is what we got. It's a nice flat line, which is sort of what you're hoping for. And this happens because we're transparent, so we get this linear behavior. But furthermore, we're reflective, so we can actually compile down our code even when it's dynamically typed. But there's a lot of important context for this, not all of which I can go into, but one thing I should in particular go into is the fact that nom is a nominally based language, whereas a lot of the things we're comparing to that I showed you earlier are structurally based languages, and this affects what we can express. So for example, traditionally, lambdas are written in this way. This is very structural style lambda. But we need this thing to have a nominal type. So even in the untyped code, you have to say, well, this is a property. So you have to say what the lambda is intended for. Now, we want to solve this. We have some ideas for how to go about improving or addressing this. But even if we don't do it, I'm happy because given our assumptions, that is, say, most code is typed, this is pretty reasonable to make. And for our applications, we'll still have a nice, efficient solution that requires some annotation burden, but also gives good performance and good semantics that we'd like. So in my mind, even if we never fix this, it's worth the trade-offs. Okay, so to conclude, first, actually, I want to thank some people. So in particular, I want to thank Fabian, my student Fabian, because he's been on this project since basically the beginning. I also want to thank the many languages I've worked with and many research groups I worked with Tate for the opportunity to be here. And I sort of want to wrap up with like what I would hope to see happen. So currently, a lot of gradual type system research focuses on the case where most code is untyped. And there's tons of useful applications for this. There's no reason to stop looking at this. But I think we could spend more effort also looking at the case where most code is typed. And what's interesting is you still arrive at the same goals, so it's not like these groups are destroying from each other, but you do end up making different assumptions. And in particular, while it's worthwhile examining how to do this for existing languages, it also seems like there's a strong need to consider how to co-design languages with gradual typing so that we can get the ideal behaviors involved. And this is going to bring you to different solutions than previous because you have more flexibility, but you can, from that, provide strong guarantees, and it seems with minimal overhead. That's it. Thank you very much, and I'm very interested to hear what thoughts and questions people have.
Thank you. Hello. I told you I would ask you mean questions, and I will. So first off, brief just advertisement for myself because I'm an egomaniac.
Go for it.
So the reason why JITs are fast is because they do structural typing at runtime. That's how JITs work. That's the reason why they work at all. And so the overheads are because of stupid implementations. There, you know, if you do the JIT correctly, it doesn't need to have a heavy overhead for structural typing. That being said, I think the more compelling argument why we don't necessarily want structural typing is that structural typing is stupid. If I have a Python library that says, you know, this argument should be a duck, it actually isn't okay for me to train a goose to quack or to honk when I say quack and shove it in and, yeah, whatever, that's good enough. But I think the sort of counter argument to that is sometimes people in the untyped portion might want to build things. They might want to make their own objects.
Yep.
And so there's this impedance mismatch of, well, I want to define things this way. So if we start with this assumption that everything is typed, does that sort of bind you when you do want to build sort of new types, new objects?
All right, great question. So one thing I didn't really focus on what you, but sort of was a high-level picture of what you said is, so here we've been viewing gradual typing as just static versus dynamic typing. But a lot of people also view gradual typing as structural versus nominal and how to mix between these two. And essentially the question boils down to, well, suppose you are willing to assume that all your typed code is nominal, but your untyped code is structural, then there's another problem that comes into play. And I mean, your stuff works on this, for example, and it's like another aspect of the picture that's great to explore. The answer is, I guess I would say, complicated, as we don't know the answer as to what the best thing is. For, say, lambdas, what we're taking advantage of the fact is that you're treating, is that you can view them as interfaces rather than as classes. And interfaces have different needs than classes, and yet still satisfy a lot of the use cases involved. For classes, I'm still not sure what the best solution is. And what I've seen for a lot of use cases ends up working fine, because by the time you, basically when you hand stuff off to your typed code, you've already had to consciously go through that process of making sure that your data is in the form that the typed code expects. And so it's not hard necessarily to make some of those steps more explicit so that that this conversion happens without a lot of magic from behind the scenes. It's, I'd say, very much worth experimenting on whether that actually is true and how often that occurs in practice, because all these things, I mean, as you see in my other work, a lot of it is analyzing what user behavior is, and it's keeping that in mind when you design your systems. So I'm totally pro for you doing more of your exploration. I'm probably going to be doing some of it myself, and I think we'll come up with very different ways of doing the same cool things. More questions?
I have got two questions. One is, you started with, you wanted to have overloading, and because it doesn't work well with gradual typing, you mutate it to multi-methods. And the question is, the first question is, do we want overloading? Gilad would have said, you know what he would have said. He would have said it breaks the beautiful erasure property that we don't want to know. We don't want types to affect the behavior of the program. Second question is, once you have multi-methods, there's a lot of problems with extensibility. What about them?
Okay, so I'm not going to answer the overloading question here because that's just way too long of a conversation. And it's not like I have a very strong belief either way, but nonetheless, I have definitely gotten the requests many times, and so I've been looking at it. As for the multi-methods, so for our stuff, basically what we do is say, so extensibility so far hasn't been a problem for us, but we have a little toy language, so deploying is another story. But at least what the evidence we have so far says it works fine. The reason is by particularly using that sort of table of general dispatcher versus specialized dispatcher. And so suppose you have A, B, C in your hierarchy, and you have some multi-method that's defined for B. And you dispatch to that statically. You say, okay, here's a B argument, go B. And now you have some subclass that extends it and adds a C case. Well then, even if they never write this, behind the scenes, the V table for that subclass would be modified to say, first check to see whether this is a C, and then dispatch that one. Otherwise, dispatch to your superclasses B. And that seems to give efficient performance and extensibility that works in the way that people still expect it to work. But as I said, we have a small toy language, so scaling to real user tests is still part of the picture. Hopefully that answered your question. Yeah, we do. You can still do this with, you can do this with separate compilation. It's not fundamentally a problem. It's just sort of like you have to look at your superclasses, and yeah, if you recompile your superclasses, well, then you have to recompile your subclasses. So that's part of the picture. But you can compile your superclasses without knowing anything about all the subclasses and the overloadings they provide. That's totally possible.
More questions?
but we should talk more about it offline.
Hi, great talk. So one of the things with overloading that you were discussing is that there's a kind of well-known way to go around the problem. Either you drop it or you do multi-method. There are other features where static types influence semantics, and if you relate to, on Monday there was this keynote by Martin Odersky where he's kind of getting at the fact that implicits are so central in the new design of Scala and so on, and those are kind of, how would you address the tension there between implicits and the challenges of gradualizing?
So I definitely don't have an answer for that on the spot. What I can say is you have to be, so type classes fall into a similar picture. And you basically have to make sure that the implicit can be generated based off just of the argument information and not the expected return type information, because you don't have the expected return type information in dynamically typed code. You only have the argument information. And so that restricts what you can and can't infer. How that affects practice, both because sometimes you can redesign your libraries around this, but also number code probably already satisfies this. Don't know. There's other parts of the picture like keeping things in scope. So if you remember my C# example where I have the enumerable .to list, that's actually normally written as an extension method. So you say start.to list. But if you run that, it just fails to execute. Not because of anything fancy like what we discussed, but because extension methods are statically resolved, and at compile time, they no longer have that information available. And so there's like, this start doesn't have a toList method, crash. Well, not crash, but runtime error. And so another challenge is keeping relevant static information around and knowing what information to keep around, and that's a whole other big part of the picture. Thank you.
I think we can have a final question from Andrew. Oh, that was didn't Andrew?
Oh. I was going to compliment you on the big orange word in the middle, and I think the co-design word. I think this is the key idea, rather than trying to push a dynamic a gradual type system into a language that was never designed to have one. Let's say, if this is a good idea, let's design a language around it. And that's actually what we're doing in Grace, but we don't really have the type expertise to make it go all the way through. But one of the things we did reject early on was the idea of overloading, not so much because it wouldn't work with gradual typing, although it doesn't, but because we're trying to design a language for teaching, and it makes programs so much harder to understand. It's a poor crutch for, you've got two different methods here, give them two different names so everyone can see they're two different methods. Or you're trying to teach the visitor pattern, which fundamentally depends on calling different methods for different kinds of nodes in your tree. You give them all the same name just to make sure no one can possibly tell which one you're using. I mean, it's stupid. So that was why we didn't do overloading. But it certainly makes trying to get this, what you call, I like the name reflective typing, that the meaning doesn't depend on knowing the types. That was a design goal too, and that follows. So we need to do more work on this, but I think getting rid of some of the bad ideas, another one you just mentioned, right, which was Java's, what are they called, add-on methods, right? Static methods that aren't really dispatched, but look as though they ought to be. If you want, you should do extensible objects, but do extensible objects right. So, co-design, excellent idea. Thank you.
Thank you.